Okay, welcome to the review video on definite integrals for the probability and statistics course. And what I want to do here is just review what a definite integral is. And we'll be able to calculate definite integrals with Wolfram alpha, but I want to review what that calculation is actually giving us, how we can interpret it. Unfortunately, my pen pad broke, and I have not yet received the replacement, so I will not be able to do the whiteboard on the screen like I've done in past videos and probably will do in the future. But instead, in this video, I'm just going to work straight with Wolfram alpha. Okay, so let's say I tell Wolfram alpha to integrate the function x from x equals 0 to 3. Okay, so first thing I'm going to note is this symbol here. I have an elongated s, and what that means is that the integral is some kind of sum. It's a way to sum up an infinite number of things where each thing has a infinitesimal thickness. And the theory behind that's really cool, and that's discussed in Calculus 1 is the main theory, and then Calculus 2 you go through some of the integration techniques. In this course, we will not be using that theory up front. Instead, Wolfram alpha will use the theory to do the computations for us. Okay, so first I want to note what that integral looks like. This is read the integral, that's the integral sign, from 0 to 3 of x dx. And what that's going to do for us is it's going to take the graph y equals x, which is graphed here. That's the line y equals x. I know it doesn't quite look like it has a slope of 1, and that's because my axes are not square. The tick marks here are further apart on the x-axis than they are on the y-axis. It takes the graph of y equals x, and it computes the area between the graph of that function and the x-axis from 0 to 3. So I got x equals 0 to x equals 3, and we see that area is represented by a triangle. And for this particular example, we could just use our geometry formulas to calculate this area fairly easily. The triangle has a base of length 3, has a height of length 3, so I have 3 times 3 divided by 2, that's 9 halves. And that's the integral from 0 to 3 of x dx. Okay, what happens if I just integrate a constant? Well, it really isn't that much different. All we've done is changed our function. Since I have a constant function, the graph of that constant function is a horizontal line, and we have the integral from 0 to 3 of 3/4 dx. Well, that's just the area of this rectangle. Okay, so I have a rectangle of width 3 and of height 3/4, so I multiply 3 by 3/4, and sure enough I get 9/4. Now what happens if I change those limits of integration? I can have a negative limit of integration, that's fine. If x ranges from -2 to 3, then we just see that this rectangle gets larger, in particular it gets wider, and now we have width 5 and height 3/4, so that the area of that rectangle is just 5 times 3/4, which is 15/4, and that's our integral. And I want to do one last example here, and that is the integral of e to the power of -x squared. And I want to integrate that from x equals -infinity to infinity. Now this time it did not draw a graph, and the reason it did not draw a graph is that I told it to integrate for all real numbers. I said find the area all the way out to the left, all the way out to the right, between the graph of this function and the x-axis. And of course we can't graph to -infinity or infinity. We had to cut it off at some finite point. But amazingly, this integral ends up being the square root of pi. And it turns out if we just do a few transformations to this function, it gives us the formula for the bell curve. And what I'm going to do is concatenate this, which means cut off these limits of integration so that I integrate from -2 to 2, and then it'll give us the graph that corresponds to this integral. And we see that indeed it does look like a bell curve. Okay. Now this integral right here, about 1.76416, okay, that is the finite area. It's this area from -2 to 2. What we just saw in the previous calculation, however, was that the area under this bell curve, even if I let it go all the way out to infinity on the right and out to negative infinity on the left, is finite. It's a square root of pi. Okay. And that'll be very useful when we study the normal distribution. But just want to point out that your limits of integration need not be finite. Sometimes if you put infinity up here, negative infinity down here, or both, you'll still end up with a positive area and a finite area. Now the way we're going to use these integrals is to first of all compute probabilities. And in the discrete case, we just added up the probabilities for the various possibilities for the function, the various possible outcomes of the function. We added together those probabilities a lot. Here we have a whole continuum of probabilities. For this normal type distribution, it has to be scaled a little bit to be a normal distribution, but it has this kind of shape. All real numbers are possible. Well, that's a whole continuum of numbers. We can't hope to add those up, even with infinite series, because the set of real numbers is not countable. So instead of using a traditional sum, we use the integral, which is the method for summing up things over a whole continuum of numbers. Okay, so that sigma sign that we used a lot in chapter 2 is now going to be changing to an integral, and a lot of the calculations are very similar. We will still have an expectation, we'll still have the variance, and really all that happens is that that summation sign just changed to an integral, and we throw on this extra dx here. Okay, so that's the introduction to definite integrals.